Welcome to the course on VLSI physical design with timing analysis. In this lecture, we discuss about standard cell library. The content of this lecture includes what is standard cell library. So, what is inside a standard cell library? The standard cell library consists of many different types of cells. So, combinational cell, sequential cells, low power cells, physical cells and power cells. We will discuss all these in detail. So, what is standard cell library? So, the standard cell library is a library of cells. Okay. So, it is used to build any kind of digital designs. So, if you can see in the left hand side you have a bunch of cells. Okay. So, we have bunch of cells are there. So, this is 1, this is 2, this is 3 and 4. So, all these are input to a EDA tool. EDA means electronics design automation, CAD means computer aided design tools. Okay. So, it goes inside the EDA tools and we have different designs in RTL. RTL means register transfer label. So, this RTL can be in Verilog, VHDL, system Verilog or many other languages. Okay. So, these two will pass through the EDA tools to generate various types of designs. It can be used in washing machine, it can be used in satellite communication, it can be used in servers, laptops, mobile phones and many other places. So, this chips IC is generated from your the layouts and layouts of the designs can be used in several places. So, one important point here I want to tell is that the standard cells are the basic requirement of any kind of digital designs. So, you have digital designs. So, the digital designs requires this standard cell library. So, we have a well defined methodology is there how this standard cell can be taken inside the EDA tools and the RTL can combine together to create your actual required implementation in the chip level. So, where we can use this standard cell library? We are talking about EDA tools. So, we have any kind of design, you can say it goes through a design specification. Let us say I want to design a processor for a smartphone, I have a specification for the processor for the smartphone. So, my main requirement there will be the power. So, let us say I want to design a processor for the server, my main requirement will be the performance. So, I have a design specification given at the design time, then I can describe that behavioral manner, describe those design specification in a behavioral description. Then we will write the RTL, whatever I discussed in the previous slide, I will describe the behavior of the design in hardware description language. So, this hardware description language will pass it through some functional verification and testing whether my RTL whatever I am writing is it correct or wrong, that I need to do that. Okay. If it is functionally working. So, their verification is of multiple types, here we are doing functional verification. The functional verification means that the RTL whatever you have written, it is working as whatever we specified in the behavioral description. So, if it is not meeting the requirement, then we will go back and modify the RTL. Now, once this RTL whatever you have written that is functionally correct, then we will pass it through a logic synthesis tool. Okay. So, logic synthesis tool what it does? We have two things, one is called logic synthesis and the second one is called physical synthesis. So, the logic synthesis converts your RTL to gate level netlist. Okay. So, this is the process of transformation of converting your RTL to the gate level netlist. So, here I have few points to say the RTL is technology independent, but the gate level netlist whatever it is generated, it is technology specific, which technology node we are designing. Okay. So, this RTL is technology independent and this gate level netlist is technology dependent. So, here in this logic synthesis tool I need this standard cell library, I need this standard cell library, because this standard cell library are designed for a particular technology node. Let us say today I am designing a processor for 65 nanometer technology node, I need a standard cell library in 65 nanometer node. Let us say tomorrow I need to design that same processor in 16 nanometer node. So, to improve the speed of the processor, I move to 16 nanometer 16 nanometer technology node, then I need a standard cell library in 16 nanometer technology node. Okay. So, in that case what we are doing is that basically we are taking a standard cell library, we may use the same RTL to generate the different gate level netlist. Why the RTL is same, but the gate level netlist will be different if my standard cell library will be different, and the standard cell libraries are technology dependent. So, here in this case we need for basically this RTL to the gate level conversion is basically pass it through a tool called logic synthesis tool. Then that gate level netlist whatever it is generated, we need to check logically verify it whether it is working as what we described behaviorally in this step. Okay. If it is working as expected, then what we need to do, we need to pass that gate level netlist to physical synthesis tool. What it will do? We have the gate level netlist as input to the physical synthesis tool and the output is the final layout. Okay. Final layout. So, what the physical synthesis tool does is basically conversion of the gate level netlist to the final layout of the overall design. So, here in this physical synthesis which is the main focus of this basically course, we go through floor planning, placement and routing, CTS, all these things to finally generate the. So, these are the steps of the VLSI physical synthesis. These steps are also called physical synthesis. Okay. Now, we will finally get the physical layout. Okay. Once the physical layout we got it, we do a layout verification whether it adhere to the rules provided by the foundry or not. So, that is called DRC check, and we also do a layout versus schematic verification. There are several types of checks are there, we do perform that. If that is not satisfied, then we need to modify the layout. And also we also look for one most important point is the timing, whether the timing of our design is meeting or not. If the timing is not meeting, then again we go back and modify the RTL such that I can get a layout which is basically where the timing is fixed. So, here the all unshaded blocks are the different levels of abstraction. Okay. The shaded blocks are the process in the design flow. Okay. The shaded blocks are basically logic synthesis is one and the physical synthesis is the two. These two are the main processes in the design flow, and the different levels of abstraction or the levels of the design representation is basically given here. Is basically this is your RTL level, the RTL level, then you have a gate level netlist, then you have a physical layout of the design. So, we have basically different levels of the abstraction, okay, and different processes in the design flow. Now, what is inside a standard cell library? Now, we are curious to know about what is inside a standard cell library. So, if you can look into this, we have so the combinational cells are there in the standard cell library. The combinational cells consists of your NAND, NOR, XOR, all kinds of combinational logics. Then you have sequential cells. The sequential cells will consist of your D flip flop, latch, T flip flop, all different kinds of sequential circuits. Now, we have little bit more cells which is needed for VLSI physical design. So, those cells are, for physical cells, one is filler cell, then the second one is the ECO filler cell, then the third one is the antenna cells. So, this is related to physical cells. Then we have power cells. The power cells are basically well taps. Then you have second one is the end caps. Then the third one is decap cells. Okay. Now, we have low power. Low power is very popular. Why low power is very popular? Because everybody is using a smartphone. The smartphone requires a low power chip. Okay. So, inside a smartphone, everybody likes that their battery life of the smartphone should be larger as possible. Okay. So, it should consume low power. So, that drives to design low power chips. Okay. So, for low power chips, we have to have multiple different things need to be considered when you are designing the chips. So, in that case, we have several things like always on buffer, then we have label shifters, then we have switches, isolation cells, then retention cells. Okay. So, these are the varieties of different techniques can be adapted to design low power ICs. Okay. Now, finally, we have some other different miscellaneous cells such as delay cells, then the tie cells, then we have clock cell or integrated clock gating cells. So, this is the variety of cells available inside your standard cell library. Okay, this low power cell is also called the power connectivity cells also. So, those are used in low power ICs actually. So, where the power is one of the main objective of our design. Then we will discuss about the combinational cells. It is very popular to design the core functionality of our design. Okay. So, these combinational cells are very useful for cells with different logic functions used to build the core functionality of the chip. Okay. So, you have different types of combinational gates are there. For example, inverter, buffer, NAND, NOR, multiplexer, XOR, XNOR. These are all low pin density cells. Low pin density means it has a few number of inputs and one outputs. Okay. But you have complex cells like full adder, half adder, multiplier, and we have more complex cells like one cell can do AND or invert. So, this is called AOI, and one cell can do OR and invert. Okay. So, that is called OAI. So, these cells are also essential for our standard cell library. So, then the question arises, if we have this first category of cells are there, why do we need this second category of cells? The reason is that if we do that logic synthesis, whatever I was talking previously, to design any kind of digital blocks, if I have this first category of the cells, then the area requirement will be higher. But if I use this other complex cells and AOI, OAI cells, the area will be smaller, because then the logic optimization tool will optimize using more complex cell. It can optimize the overall design using more complex cell. And what is the basically there will be some limitations are there, like you have high pin density, because if you have more number of pins, then there is a problem with the routing. Okay. So, to avoid routing, what is the strategy applied is that we need to add some kind of pad cells before and after those complex cells, in case there is some kind of routing congestion. Okay. So, it is better to add padding cells to avoid routing congestions. Okay. So, this is all about the combinational cells. This is we will discuss about how we can design it actually. So, let us say we have a stick diagram, we have a inverter. Okay, we have a inverter, this is the inverter, everybody knows, This inverter consists of two transistors, NMOS and PMOS. This is PMOS, this is NMOS. Okay. So, this is in, this is out. Okay. So, what here it is drawn is that it is showing the dimensionless layout of the inverter, and here it gives the way at which you can draw the layouts. Okay. So, if you can see here, so you have a VDD here, you have a ground here. So, this is called the schematic actually, this is called the schematic, and this is the stick diagram, which is not the actual layout, it is independent of any technology node, but this stick diagram give you the guidance how we can do the layout. Okay. So, if you can see here we have a VDD here. Okay. So, we have a VDD line is there. Similarly, one ground line is there, one track is assigned for the ground. Okay. Now, we have this is the in pin, this is the in pin. So, in is connected to your the gate of the transistors. Okay. So, this red line says that both the gates of the transistors NMOS and PMOS are connected. So, these are the gates. Okay. Now, if you can see here we have a source pin of the NMOS, this is the NMOS. Okay. The source pin is connected to ground. So, if you can see you have a contact, this is called a contact, which is connected to ground. Similarly, you have this is your source pin connected to ground, this is the source. Okay. Now, we have this is gate and this is drain of the NMOS. Drain is connected to your output. So, this is your drain. So, if you can see here this green color line shows the NMOS represents the NMOS and this brown color line represents the PMOS. Similarly, your source of the PMOS, this is the source of the PMOS is connected to VDD through a contact, okay, and your drain is connected together to create the output pin. So, this is a technology independent dimensionless layout strategy, which gives the designer how to do the layout efficiently with less area. So, this stick diagram can be used to do the layout of an inverter. Okay. So, if you can see here in the first case, okay, you have basically this is your ground line, this is your VDD line, okay, and from here to here is your NMOS and here to here is our PMOS. Okay. Now, in the first case, in the first layout, this is the first layout, this is second, the third, and the fourth. In the first layout, VDD and ground is drawn and you have NMOS and PMOS is placed. In the second case, what was done? NMOS source is connected to the basically ground, PMOS source is connected to the VDD. Now, we have basically both the gates are connected and both the drains are also connected, both the drains are connected. But if you can see here, this layout will functionally work as a inverter, but it is not the best layout. So, what they did? They extended the metal, okay, extended the metal in both the direction to make a bigger contact, okay, to make a bigger connection between the diffusion and the metal. So, then what happens is that the more contacts are placed in the fourth layout, more contacts are placed in the fourth layout. So, if you can see here, this is your power rail, VDD ground rails are the power rail and this VDD and grounds are the power rail. One of the main point of the standard cell library is that all the cell height is same height. The reason for that, all the cells, even if it is a NAND versus a D flip flop, all the cell height is same or multiple of that height. Either all the cells have same height or multiple of the unit height, multiple of the height of minimum height cell. Okay. Either all the cells will have same height or it can be multiple of that minimum height cells. Okay. One advantage is that the power grid is created automatically. The power grid is created in metal 1 automatically. So, which will provide uniform power to the each of the cells. This is one of the most biggest advantage of keeping all the cell height same. Okay. Now, what happens is that we are talking about the sequential cells. In case of sequential cells, we have flip flop and latches. The flip flops they can have D flip flop, SR flip flop, we have D flip flop, SR set reset flip flop, which is most commonly used in several designs. Okay. This flip flop can have two different flavors. Okay. Before going to those flavors, your flip flops are edge triggered, and you have latches which is label sensitive. In the flip flop case, your signal can be captured either in the positive edge if it is a positive edge triggered, or it can be sampled in a negative edge if it is a negative edge triggered flip flop. So, this is positive edge triggered, this is negative edge triggered. So, depending upon the requirement, you can design positive edge triggered flip flop and negative edge triggered flip flop and keep it inside our library. Some cases the positive edge triggered is required, some cases negative edge triggered is required, then the synthesis tool will pick based on the requirement. Then we have latches which are label sensitive. You have positive label sensitive latch and negative label sensitive latch. Positive label sensitive, positive label or negative label sensitive latch are there. So, now we are talking about flip flop and latches. Now, we can talk about there are scan flops. What is this scan flops is that whenever you are designing any kind of digital system, we want to check, we have very fewer number of pins are there, but we are interested to know what is happening at each and every point of the chip. The reason is that if the chip is not working, how can I debug any part of the chip? What is the value of the nets inside the chip? So, for that purpose we have to insert scan flops. Okay. So, all these flip flops can have basically converted to scan flops. Normal flip flop to the scan flop conversion can happen during the synthesis flow, logic synthesis flow before the design for test. DFT stands for design for test. So, there is a best practice to check flop placement distribution quality before proceeding for the this is called clock tree synthesis. So, now this latches, what is the use of the latches? It is used in the timing path and it is also used in clock gating usage. Clock gating cells also we can use the latches, and this lockup latch is in the scan chain can be used to reduce the clock skew problem when we are dealing with different types of clocks inside a complex design. So, there is a concept called multi-bit flip-flop. Okay. There is a concept called multi-bit flip-flop. What it does is that it is created by combining multiple single bit flip-flops. Okay. So, if they are sharing a common logic and power supply, if there are multiple flip-flops are sharing a common logic and power supply, we can replace those flip-flop with a multi-bit flip-flop. It comes with different flavors like 2 bit, 4 bit, 8 bit, 16 bit like that. Okay. It has multiple height or row cells, it can have multiple heights whatever I told you. Sometimes you have multi height cells, but the height should not be any random numbers, it should be multiple of the minimum height cells. Okay. Your height of the cell is well defined whenever we are designing the standard cell library. The standard cell library design architect will decide what will be the right height for the cell. Then it will reduce the area. What is the advantage of this one? It reduces the area, this is the first point. It reduces the clock dynamic power, the second point. It is used for better clock skew, the third point. Then the fourth one is the timing improvement, it has better timing improvement. But what is the, these are the advantages. And what is the disadvantage of the multi-bit flip-flop is that whenever you have any kind of design issue because of the timing of any one of the flip-flop inside the multi-bit flip-flop, then what we have to do is that we need to break that multi-bit flip-flop and create the single bit flip-flop again to meet the timing. So, this is the basically how the multi-bit flip-flop will look like. Here there is two single bit flip-flop, this is one and this is the second, this is the first one, this is the second one. Then it is combined to create a 2-bit flip-flop. If you can see here, the clock is going to all of them together. So, the dynamic power is reduced and basically area is also reduced, and you have two data input D1 and D2, and you have a clock pin and you have two output Q1 and Q2. So, this is the architecture of multi-bit flip-flop. Now, we have different physical cells. The physical cells are needed for DRC closure. So, basically if you can see the filler cells, okay, the filler cells are used to fill the empty space and provides the continuity of n wells. Okay. So, basically it will allow continuity of n wells. Let us say I have one row of standard cells, this is the VDD and this is the ground, this is VDD, this is the ground, and let us say the inverter is sitting here, I am writing INV. Let us say this is NAND gate is sitting here, just it is a I am not drawing to the scale. NAND gate is little wider than inverter, okay, this is NAND 2. Then if there is no cell is in between, your n well continuity is lost. To make the n well continuity and also the power grid continuity, you have to put filler cells here like this. So, this filler cell has no transistor inside it, only it is used to basically create the continuous n well and continuous power grid, and this is useful for cleaning the DRC errors. Okay. It will also help to clean the metal density rules needed at the latter stage of the place and route phase. Basically, if you can see here, there is a strategy is that whenever you are filling the cells, we should always use the bigger cell faster than smaller cells. So, the filler cell also comes in different flavors. So, the smaller one is 1x, then the wider one is 2x, 4x, 8x, 16x like that. Whenever you have more vacant space are there, the bigger means 16x cell will be inserted more. Then when the smaller space is there, then the 1x or 2x cells will be inserted later. So, why it is needed? It helps in also removing the DRC violations in less time. Then we have a ECO filler cell. It is very important. The ECO filler cell, it is a cell basically at the design, whenever you are designing the chip, it is inserted. Okay. While we are designing the chip, these ECO pillars are inserted, but it is not connected with the actual any of the nets. Okay. But what happens is that if they, let us say there is some kind of issue latter part of the design, so these cells can be programmable. So, it is a programmable ECO cell. What it does is that you can connect metal 1 and metal 2 routing layers, okay, metal 1 and metal 2 routing layers to create a logic. Okay. So, if there is a some functionality is not working in the final chip, then we can redesign the cell by connecting the metal 1 and metal 2 routing again, and we can save the cost of refabricating this chip again. For example, let us say I have a VDD and this is the ground, this is VDD, this is ground. I will give you an example here. Let us say I have some cell there, this is a ECO cell, ECO pillar cell. This is another ECO pillar cell is there. So, let us say I have a hold violation is there. Okay. So, in case of hold violation, I need to add some more delay to the combinational path actually in between the flip flops. So, what we can do? We can take the output of the flip flop and connect to the input of this cell. Let us say this is a ECO buffer cell actually. So, you can connect the output of the flip flop to the input of the ECO filler, then you take the output here and connect it. If you multiple fillers are needed, then you connect it back to the another flip flop. So, this is the flip flop, first flip flop output, flip flop 1 output and flip flop 2 output. This is the launch and capture flip flop. So, in this case we are adding delay to the actual critical path, and what is the advantage of this one? We are just adding some metal lines. So, these are in metal 1 and metal 2. Okay. These are all in metal 1, I can draw it in a different color to distinguish that. So, these are in same metal. So, here what we are doing, this can be any metal, but we are using just for example metal 1 and metal 2. This ECO filler is acting as a buffer, but there is also ECO filler with a different functionality also. We can use different metals and create different functionality. If my logic is wrong, I can resynthesize the RTL, add some new logic and reroute the design such that my circuit chip can work again. So, what is the advantage is that we do not need to fabricate all the mask layer of the chip, only the layer at which these modifications are done, let us say in the metal 1 and metal 2, those masks need to be recreated. So, this is very useful if there is any kind of bug is there during the chip design. So, now we have another physical cell which is called the antenna cell. Okay. So, these antenna cells are used to fix the antenna violation. What is this antenna violation is that whenever you have a NMOS transistor or PMOS transistor which is connected to a very large metal, okay, metal 1, long metal is connected to this gate actually. So, what it does is that basically it accumulates more charge, okay, and that can damage the gate of the MOSFET, because this big piece of metal can accumulate charge, and the charge it will not able to get a discharge path, and it will damage the logic gate of the MOSFET. To avoid that, what people do is that there are two ways to solve the problem. One solution, this is the problem, antenna violation problem. The first one is the antenna violation problem. The first one is the antenna violation problem, and the second one is basically metal hopping. Okay. So, we can hop to different metal from metal 1 to metal 2, this is metal 2, okay, this is metal 1, such that this problem can be solved. This is one, metal hopping is one solution, and this is first solution, this is S1 the first solution, and this is the second solution, this S2 is the odd antenna diode, odd an antenna diode to the gate of the MOSFET. So, this diode if you add, then it will find the discharge path through the reverse bias diode. So, then the antenna violation should not happen and it will not damage the gate of the MOSFET. We discuss about standard cell library, its usage and content of the standard cell library. Thank you for your attention.